to details, I would like to present relevant background and my motivation for this thesis. Then I will present two of my works, Smoke and Very Build. Both are designed for tackling the challenges of adopting static code analysis in practice. We summarize this presentation at the end. Today's software system sizes are expanding at a furious speed. For example, the Firefox browser now has more than 9 million lines of code. Despite the size expansion, those systems show a trend in constructing complicated dependencies among modules and libraries, which results in the continuous growth of the complexity. Along with the growth in size, the number of program errors have also dramatically increased. Some can even cause serious damages, such as the recent bug in the Boeing 737 MAX Airjet, which has killed over 300 people. According to a report from McConnell, for typical software, the estimates are up to 25 errors per assembly line. And nearly two-thirds of vulnerabilities come from simple programming errors. And program errors are so common and they cannot be completely eliminated. This is why almost every software project has its own bug tracking system. Among various approaches to detecting program errors, static analysis can reason program behaviors without running them. NIST, the U.S. National Institute of Standards and Technology, emphasized the power of static analysis by stating dramatically reducing software vulnerabilities. Compared with dynamic analysis, static analysis can be deployed earlier in the software development lifecycle. And compared with human eye, it is more reliable and incurs lower cost. However, in practice, static code analysis does not perform very well as we expected. First, it's not popular. According to a survey, only 37% of all top-rated GitHub projects actually enforce static code analysis. And according to our own experience, the industrial adoption rate should be even lower. Second, even for those organizations that have deployed static code analysis, their degree of deployments are also disappointing. Around 88% of organizations use static code analysis only for checking styles and naming conventions. Thus, we are curious about what causes this situation and what should we do to improve it. So what's the best way to study a problem about practice? We invent our own static analysis system and try to get it deployed by as many users as we can. We start our own journey of practical static analysis in 2014, and this project involved several PhDs and approximately 10 engineers. We have developed Pinpoint from scratch, which by now has been adopted by more than 30 different organizations. My roles in this project include algorithm R&Ds, software engineer to develop systems for integration, and to deploy static code analysis for some of our users. And my main focus of this research is to make static code analysis practical. Along with this journey, we have summarized some of our research ideas into publications, and I have included two of them in this thesis. The first one is Smoke, a scalable path-sensitive memory leak detection for millions of lines of code. And the other one is Very Build, which is designed for verifying dependencies in build scripts. At the first glance, it seems that these two works have no direct relation. One is a static analysis algorithm, while the other one is a systematic work for build systems. I chose them because they are two representatives of the two greatest challenges we have encountered for making static code analysis practical. One is scalability, and the other one is integration. So what's acceptable scalability in practice? This was our question at the beginning of this journey. We used to think that 1 million lines of code is very large, and this is agreed by many researchers as well. However, in practice, only 100 millions of lines of code is considered large. We used to think that static code analysis that can finish with overnight time is very good. However, in practice, people think 2 hours is too long. 1 hour is too long, and maybe 10 minutes is acceptable. And the 10 minutes is the exact time requirement when we are deployed our approach in Baidu. We used to think 40 core machine is normal. Since we have many such machines in our lab, and the internet companies are rich. However, what we offered from the WeChat was a dual-core machine with 2 gigabytes memory. And they also asked, can we run our analyzer in a virtual machine? We used to believe that precision and scalability are trade-offs. However, when we talked this up, with a user in TCL, their reply to this is no. For us, they are not. We chose to study the memory leak detection for better understanding the scalability problem in static code analysis. We chose it because it is a well-studied problem in research, and also because it is a crucial problem. It can slow down applications, can crash long-running programs, and can even lead to security vulnerabilities. And in industrial scale, it is pretty much an unsolved problem. In 2017, more than 600 memory leaks are reported in Firefox and Chrome, and in the same year, more than 240 CVE entries are directly related to memory leaks. The other greatest challenge is integration. Our conclusion for integration is that no integration means no adoption. Some users will not use a tool if it is not integrated, since it costs a lot to learn the usage of a new tool and also takes a lot to use it. Some users are willing to use your tool, but they cannot use it if the tool is not integrated with their systems. For example, if not integrated, you cannot even touch their code due to their security policy. And you have lots of systems to integrate with, such as the access control system, code repositories, and all kinds of systems in DevOps. Among those systems, build systems are the most important. Build system is a crucial part of a software system. It could impose 12 and 36% overhead on software development. And usually, build system is consisted of two parts: the build tools, such as Make, Sconce, Bazel, Ninja, and the other part is their build scripts, such as Makefile, build.ninja, and Pom. Two well-known features of build systems are incremental build and parallel build. Build systems play a vital role in static code analysis, and we believe its importance is generally undervalued. Most static code analyzer for C and C++ relies on build systems to extract the source files, the compiler versions, and the options. They also rely on build systems to extract the dependencies among different components. If a project cannot be built, then it cannot be analyzed either. If a project build is very slow, then the time cost for a code analysis is the time of running algorithms plus the time for build. If a project build contains error, then it can lead to incorrect analysis results. The good support of build systems is one of the reasons that why WeChat selects Pinpoint over other static analyzers. This is why I selected these two works in this thesis. The eager to make static code analysis practical motivates these two works. Let's first talk about smoke, a scalable approach to memory leak detection. Many static approaches have been proposed to detecting memory leaks. The basic idea for static approaches to detect memory leaks is to find feasible program paths from the allocation side to the program exit that do not pass through a deallocation site. Different static approaches work with different precisions. A flow-sensitive analysis takes into account the order of statements in a program. And a path-sensitive analysis takes into account the feasibility of different program paths. Roughly, a path-sensitive analysis is much more precise than a path-insensitive analysis. Path-insensitive approaches are considered scalable. However, they are also imprecise. The right side shows a leak-free example. The memory object is allocated and freed under the same condition. A path-insensitive analysis cannot recognize such cases and report lots of false positives. In our experiment, Saber, a recent flow-sensitive but path-insensitive approach, has a very high false positive rate of 66%. Path-sensitive approaches are precise, however, they have scalability issues. Some path-sensitive approaches reduce the problem of finding memory leak paths to constraint solving problems, and use a sledgehammer, the SMT solvers, to solve them. Other path-sensitive approaches symbolically execute the program, path by path, and also use solvers to resolve the path conditions. Such approaches will encounter two problems. The first, as we all know, is the path explosion problem. The second is that constraint solving is expensive. The more you use, the less efficient your approach will be. Setter is reported to spend 23 hours for checking a project with 5 million lines of code. In addition, we have implemented a memory leak detector based on value flow analysis in Pinpoint. Even with the improvements we have made in resolving the pointer trap, it still failed to detect leaks in many large projects in 2 hours in our experiment. Let's summarize the problems of existing approaches. Path-insensitive approaches are scalable but imprecise. Path-sensitive approaches are precise but unscalable. Together, they form the scalability and precision paradox. Our goal of research is to resolve this paradox by designing an approach to memory leak detection that is both scalable and precise. Our approach is based on observation that in practice, most memory objects are managed safely. Programmers only make mistakes for some memory objects instead of all, and most of those safe cases can be identified by a flow-sensitive analysis. Such as the example shown on the right side, the allocated memory is freed in all its outgoing passes. Those deallocation sites together post-dominate the allocation site on a control flow graph. In our experiment, around 99% of all the memory objects can be identified to be safe with a flow-sensitive analysis. However, existing path-sensitive approaches analyze every memory object in the precision of path sensitivity, which causes scalability problems. This observation inspires us to design a staged approach for achieving both scalability and precision. In the first stage, we use a flow-sensitive analysis to quickly prune safe cases, and we only perform path-sensitive analysis for those cases that cannot be identified as safe in the first stage, which accounts for later part of all the cases. Okay, let's first talk about how to design a lightweight flow-sensitive method for pruning safe cases. Traditional data flow analysis can be used for analyzing memory safety. It assumes a memory object can have four states: uninnate, allocated, freed, and leaked. Based on this assumption, it uses the classical Kita algorithm to inference the states of a memory object, and the algorithm runs in polynomial time. However, their approach is not efficient since it analyzes every program statement, no matter whether the statement can affect a memory object's state. For simplicity, in this presentation, we refer to this kind of data flow analysis as a memory state analysis. Saber and FastCheck are two recent flow-sensitive approaches that are based on sparse value flow analysis. Their design is motivated by an observation that memory objects are used sparsely. Most of the program statements cannot affect the state of memory objects. Thus, they track the value flows sparsely via data dependencies and skip irrelevant program statements to achieve scalability. However, they are still not efficient. For example, in our experiment, Saber failed to analyze most large projects in 2 hours. So what makes them inefficient? Sparse value flow analysis works on a data structure called the value flow graph. It is constructed by identifying the definition sites and the use sites of a memory object first, and then connect them based on the def use chains. However, you cannot perform the memory state analysis directly on a value flow graph. For example, we have two cases here. One is a leak-free and one is not. However, the value flow graph corresponding to the two cases are identical, which means that you cannot differentiate those two cases with only the value flow graph. It lacks sufficient information for analyzing them. Specifically, it lacks two kinds of information for performing a memory state analysis directly. First, it lacks some statements that can affect the state of a memory object, such as the return statements. They are not definitions and they are not use-sites either. Second, it lacks the control flow orders among those statements. It is important to know which statement executes first, the return statement or the free set. Since a value flow graph lacks the two kinds of information mentioned previously, to detect memory leaks, the existing sparse value flow analysis has to recover with constraint solving. First, it constructs a value flow graph, and then solves this equation to find memory leaks. Let's use an animation to illustrate its underlying technique. The first component of this constraint is to collect the path condition from the allocation side to the first free side. And the path constraints are collected by visiting all program paths between the allocation side and this free side. It does the same for the second free side. The disjunction of them means to select all paths from the allocation side to all the free sides. Then it does a negation, which finally finds the leak path in this control flow graph. The existing sparse value flow analysis are basically enumerating all program paths with constraint solvers, which will definitely encounter the path explosion problem, and you cannot expect high performance from that. Can we design an approach that keeps the sparseness but does not come with the path explosion problem? Can we combine the sparse analysis with the traditional memory state analysis? We address the limitation of the value flow graph by designing a new sparse data structure, the use flow graph, on which we can perform data flow analysis directly. First, we identify the program statements that may cause the state changes for a memory object. Those include the allocation site, the free sites, and the program exit. Then we create a node for each of them in the use flow graph. Instead of using def user chains, we use the control flow orders among those nodes as the edges. A nice property of such approach is that the edges in the use flow graph support the propagation of memory states due to the nature of control flow orders. This nice property enables us to use a simple memory state analysis to analyze the safety of a memory object. For example, the allocation site generates the data flow fact allocated, then propagated along with the use flow edges. When meet a free site, we kill the allocated fact and generate a new state freed. Both the leaked and the safe fact can reach the program end. The result of analyzing the state of this memory object is may leak. We have illustrated how to use the use flow graph to detect a leak case. Now we use a safe case to further illustrate the difference between our approach and the sparse value flow analysis. Here's an example that is memory leak free. The memory object allocated line 2 is freed by the free site at either line 5 or at line 8. For a sparse value flow analysis, it will first create a value flow graph and then use a constraint solver to solve this equation to prove that this memory object is safe. Note that the path conditions for real programs are much more complex than we used here in this equation. With the use flow graph, we can simply propagate the states along with the use flow edges. The memory object will always end in a safe state. Remember that we are able to use this simple efficient analysis to prune 98.6% of all memory objects. Okay, after identifying all the safe cases, let's deal with those leak cases. There still exists a handful of cases that require capturing branch correlations. This example is leak-free because the memory is allocated and released under the same condition at line 3 and line 7, respectively. However, the sparse value flow analysis will mistakenly report it as a memory leak due to the negligence of the branch correlations. To correctly identify that the code snippet is leak-free, we employ a staged constraint solving process to verify the feasibility of the candidate leak paths. First, we adopt a linear time solver to filter obvious invisible passes, such as the pass condition above that contains obvious contradicts. Most of the false warnings involving branch correlations can be pruned at this stage. For the remaining passes with complex pass conditions, such as this example, we adopt a full-featured SMT solver such as these three to check their feasibility, hence achieve a low false positive rate. Okay, let's summarize our approach based on the limitation of the current sparse value flow analysis. For sparse value analysis, since the value flow graph is not capable for memory state analysis, existing sparse value flow analysis has to enumerate passes on a control flow graph to analyze the memory state, which is inefficient due to the pass explosion problem. Well, for our approach, we first propose the use flow graphs that support propagation of memory states, and then use a flow-sensitive memory state analysis to prune safe cases, and use staged constraint solving for checking pass feasibilities for the remaining cases. For evaluation, we implement Smoke as a tool based on the LVM framework. We compare Smoke to tools from both academia and the industry. SVF and Pinpoint are the state-of-the-art approaches based on sparse value flow analysis, and the Class Static Analyzer and Facebook Infer are two representative open-source bug-finding tools. We select 29 subjects from both popular open-source projects and standard test suites. The sizes of this program range from a few thousand lines of code to close to 8 million lines of code. The top three programs in size, Firefox, are commonly used browser, Wine, and Blender. We compare the analysis time cost of all tools. On average, Smoke achieves the best efficiency and is significantly faster than other tools. It is 5 times faster than SVF, 13 times faster than Pinpoint, 12 times faster than Class Static Analyzer, and more than 23 times faster than Infer. We've demonstrated the scalability property, and we would like to evaluate its precision and recall as well. And to evaluate its precision and recall, we manually inspect all the results and classify bug reports as false positives and true positives. This process could be subjective, so we tried our best to be objective, and we also released our results online for further inspection. On average, Smoke achieves a false positive rate of 24.4, which is the lowest one among all the tools. To better understand the usefulness of Smoke in practice, we seek confirmations from the original developers of the subjects. Since we cannot flood them with all warnings, we manually pre-screen the bug reports and choose only those that are likely to have severe impacts. All 30 reports get confirmed by their developers and result in many patches and bug fixes. A memory leak that Smoke find in BFDD is severe enough to be assigned with a severe ID. Before presenting the next work, please allow me to share a real story with you. At a time of this journey, we are quite happy with our progress in resolving the scalability problem for static code analysis. A user reported that the static code analysis for his project runs for more than 5 hours. After the investigation, we found that it is due to its slow sequential build, which costs for 4 hours. The user could not enable the parallel build, which runs much faster than a sequential build, due to a build issue. So we start to investigate this issue since it slows down the whole static code analysis. We came up with the idea to skip it. Instead of using the build command make directly, we create a shell script to run make 3 times. First, we run the build in parallel until it is crashed. Then we run the build sequentially to skip the dependency bug. After around 1 minute, we guess that the bug is skipped. So we kill the build process and rerun the make in parallel again. This is our solution for their problem. By coming up with such a nasty, unreliable, and inelegant bug fix, we think we somehow damage the reputation of HQST. This motivates my second work, VeriBuild, an approach to verifying build dependencies. What we encountered in that company is not just an exception. Build issues are ubiquitous due to its high churn rate. A survey showed that more than half of the 30 surveyed commercial projects had a clean serial build time of 5 to 10 hours, and most organizations run their builds completely sequentially. Among various kinds of build errors, dependency-related errors are the most common. It consists of two major categories: missing of dependencies, which can lead to parallel build failures or incorrect incremental builds; redundant dependencies, which can lead to downgraded parallel and incremental build. We use an example makefile to show the basic concepts in the build scripts. Makefile specifies the dependency among targets. The left side of the column is the name of the target. A target is not necessarily a file. For example, we have target names such as install, test, and clean. And to the right side are the prerequisites of the target, followed with one or multiple commands for building the target, which we call them its recipe. Makefile declares the dependencies among targets, which we call them the declared dependencies. For example, this line indicates a declared dependency from the generated.h to the target config. For the dependencies happened for actual build, we call them the actual dependencies. For this recipe, the execution of this command requires the presence of a file, which is a config. So the target generated.h also has an actual dependency onConfig. The basic idea for verifying dependencies is to cross-check actual dependencies with declared dependencies. Static approaches construct the static dependency graph via statically analyzing the build scripts. However, they do not have the actual dependencies to compare with. So what they do is to guess the possible file reads and writes from the command line options. Of course, such approaches are not reliable, since many file inputs and outputs cannot be extracted from options. For example, can we guess the inputs of this command? To obtain the actual dependencies, Bessemer constructs the dynamic dependency graph from system call tracing. For example, for a file read, it will create a data dependency from a process to a file. And for a file write, it will create a data dependency from the file to a process. While all the file operations in between, we can obtain the dependencies among files. And then the approach compares it with the static dependency graph from parsing build scripts to detect the inconsistencies. However, the approach has lots of false positives due to two reasons. First, as we have mentioned, targets of files are incomparable, since a target is not necessarily a file. Second, their declared dependencies extracted from script parsing are incomplete. Their static dependency graph lacks the implicitly declared dependencies, and all implicit declared dependencies are mistakenly identified as missing dependencies in their approach. So what are implicitly declared dependencies? We use an example to explain it. For the first rule, it specifies a declared dependency from for to target lib. If you look at the command line, the execution of its recipe will read a file named lib4.a, which is a static library. However, lib4.a is not specified as a prerequisite of target for. So its lib4.a is a missing dependency of target for? No, it's not. You cannot trigger any build issue with it. And this is an example of false positives that the Bessemer approach will report. Because when declaring the dependency from for to lib, the build scripts implicitly declare a dependency from the target for to all the output files of target lib, which is lib4.a. To obtain the complete declared dependency, Laker and Rice proposed build fuzzing in 2019. Similarly, it traces system calls of an actual build for inferencing the actual dependencies among files. And then, to inference the full declared dependencies, it repeatedly triggers incremental build for each source file in a project. Let me use an animation to illustrate how it works. Build fuzzing first builds the project once, so that any modifications in a file will trigger an incremental build. To extract the declared dependencies for one file, it first modifies the input file's content. The build system will calculate the dependencies and selectively build all the targets that depend on this file. After the build, it collects all the output files that have just been modified. Those files that are modified are those that have declared dependency on this input file. It repeats this process for each source file until all its input files are fuzzed. The problem with their approach is that incremental build is not cheap. For example, the time cost for incremental build of LLVM is more than 38 minutes, and LLVM has more than 40,000 input files in total. In our experiment, their tool MakeCheck spent 53 hours on analyzing OpenCV and failed to analyze LLVM and OpenSSL in 60 hours. As a comparison, our approach for the same three projects runs only 10 minutes, 1 hour, and 6 hours. We can conclude that using build fuzzing to extract declared dependencies is not practical. Can we find a better way to extract the declared dependencies? What we want to know is that for a file and a target, is there a declared dependency between them? Let's recall what we can get with the existing approaches. For this target, with script parsing, we know all its prerequisites. We can also know the recipe for building each target from the script. And with system call tracing, we know which process actually generates this file. If we can find a method to bridge the gap between a recipe and the processes, the whole graph is connected and we can detect the declared dependency from this target to this file by search the graph. We propose building instrumentation for resolving this problem. Remember that we can have the static dependency graph from script parsing. With it, we can have the recipe of any target. Instead of system call tracing a build as if it is a black box, we can initialize a process for each of the targets. In this way, we can know exactly which process is initialized for which target, so that all file reads and writes happen in this process and all its child processes are the file reads and writes of this target. Okay, let's summarize our approach. Our approach consists of two steps. First, we use script parsing to extract the static dependency graph, which is similar to those static approaches. The second step, we propose a new method called the building instrumentation that the instruments and traces are actually built. Most importantly, we can inference the implicitly declared dependencies from the instrumentation together with the actual dependencies. We use a novel graphical representation called the unified dependency graph to record all three kinds of dependencies, with which we are able to reduce the problem of detecting dependency issues to graph queries. We further use an example to extract it from a real open source project MPC to demonstrate our approach. This example contains both missing and redundant dependencies, and we are going to find them out after a few minutes. First, we will build the static dependency graph. Basically, the nodes represent all the targets and the edges represent the dependencies. Next, we start to execute the build instrumentation. First, we topologically sort all the graph, and then do build instrumentation in the reversed order from leaves to the root. For each leaf target in the graph, we check whether there is a file with the same name presented in the file system. If so, we create a file node corresponds to it and create a black arrow from the target to the file node. Then we extract the commands for building a target and execute it with system call traced. For example, here shows the command lines for building target test static. We execute the command with system calls traced. After the execution, we detect that this command reads two files, test.static.c and lab.mpc.a. At the same time, creates one file, which is build test slash test static. We create a file node for each file appeared in the trace. For each read, we create a blue dotted arrow from the target to it. And for each write, we create a red arrow to it. Similarly, we conduct the build instrumentation for the target test file, which creates four more edges and three more file nodes. Finally, we conduct the build instrumentation for the target check, which adds two more blue edges. Now we have finished constructing the unified dependency graph. In this graph, all the solid arrows represent the declared dependencies since they are enforced by the build scripts, while the blue arrows represent the actual dependencies between a target and its input. Detecting errors with unified dependency is straightforward. To detect a missing dependency, we compare declared dependencies with the actual dependencies. In the graph, in order to check whether the target check has missing dependencies, we first collect all the file nodes that are reachable from target along with solid edges, which are these three file nodes. And then we search the graph for all the file nodes that are reachable from target test file along with the blue dotted arrows, which are one file. With this approach, we can detect the test file has two missing dependencies. And to detect whether a dependency is redundant, we test whether removing it could change the actual dependencies. Let's take the dependency edge from test file to test static as an example. Before removal of this edge, one file node, test file.c, is reachable from test file, along with both kinds of arrows. We then remove this dependency edge, and this file is still reachable from test file along with both kinds of arrows. Thus, we can conclude that this dependency is redundant, and we can safely remove it from the build script without affecting the declared dependency relation for target test file. For evaluation, we implement our approach as a tool called varibuild. We have implemented 4 checkers on it. The 2 more checkers are implemented for demonstrating the extensibility of the unified dependency graph, and you can find more details in the thesis. We compare varibuild to the state-of-the-art MK check over 42 different open source projects, and we set the timeout to be 60 hours. Here we show the information of all the 42 subjects. It includes very large projects such as LLVM, OpenCV, and Python, as well as projects used in the evaluation of MKCheck. We support both Make-based projects and Ninja-based projects. For efficiency, we compare the time cost of both tools. On average, varibuild is 26.5 times faster than varibuild and incurs 58.2 times less overhead. As we have mentioned before, MKCheck spends more than 50 hours for 3 large projects. As a comparison, our approach spends only 10 minutes, 1 hour, and 6 hours for the 3 projects, respectively. For the effectiveness, we manually and automatically classify the report issues to true positives and false positives. A missing dependency issue is a false positive of it cannot be used for triggering incorrect incremental build. And a redundant dependency issue is a false positive of removing it could result in incorrect build. Our approach is able to detect more than 1,902 missing dependencies and more than 200 redundant dependencies. And our results supports MKCheck in 25 of 38 projects. To further evaluate its effectiveness, we have submitted all the reports for projects with less than 100 reports to their developers. By the time of writing, 398 out of 700 submitted reports are confirmed. Okay, I have finished presenting the 2 approaches. Let me summarize this thesis. This thesis focuses on the practical aspect of static code analysis. Specifically, we focus on 2 greatest challenges for adopting static code analysis in practice: scalability and integration. For resolving the scalability problem, we present SMOKE, a two-staged approach for memory leak detection. It uses the staged design together with sparse analysis techniques to achieve excellent scalability. And for resolving the integration problem, we present Varibuild, an approach to verifying the correctness of build dependencies. It uses static analysis to complement conventional dynamic approaches for constructing a unified dependency graph, which facilitates efficient and precise detecting dependency errors via simple graph traversals. Of course, being practical is not only about two approaches. Our journey is to be continued. Thank you.